Alright, so getting into the 10.3 material here. So 10.2 is where we talk about arcs, so that's what we'll get to next time, but I should mention, because this comes up in our vocabulary a little bit here, so an arc is just the path between 2 points on a circle. So a major arc is the longer path around the circle between the 2 points, a minor arc is the shorter path between the 2 points on the circle. And if it's exactly half the circle, then it's called a semicircle. So for this first theorem, in the same circle or in congruent circles, minor arcs are congruent if and only if their corresponding chords are congruent. And remember, if and only if means that it works both ways. So if I know that the arcs are congruent, that means I know that the chords are congruent. And conversely, if I know the chords are congruent, that means I know the arcs are congruent. And this symbol is what we use for arc, so that would be the line segment. And then we use this nice curved thing for an arc. So RS, arc, is congruent to arc TV, if and only if the chord RS is congruent to the chord TV. So let's look at that in this example real quick here. So it's given us from these markings that these two arcs are congruent, and by this theorem that means I know that these two chords also have to be congruent. So I can set up an equation to find x, and remember x is part of what I need, but really AB is what I'm looking for. So we want to make sure we know what we're checking here. So 8x is equal to 2x plus 3. Got to get all my x's to the same side. So that gives me 6x is equal to 3. And then I divide by 6, and I get that x is equal to 1/2 or 0.5, whichever way you want to think of that. But remember, I'm not done, because what did it ask me to find? AB. So I need to now plug this in here. So AB was 8x, so that'd be 8 times 1/2 or 0.5. So the length of AB is equal to 4. Alright, so let's look at a few more theorems about chords. So perpendicular chord bisector theorem. So if a diameter, or radius really, so it technically says diameter, but a lot of the time they won't give you a full diameter. They'll just show like this part of it. So if a diameter or radius of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So if I were looking at this diagram right here, then that would mean that this diameter WZ, because it's perpendicular to those two chords, bisect AB and also bisects RS. So I would know that those parts are equal. It does also bisect the arcs, AB and RS, but we're really not going to talk about arcs much right now. That'll be more for next time. So then the converse of that would be that if one chord is a perpendicular bisector of, that's kind of funky looking, alright, perpendicular bisector of another chord, then the first chord is a diameter. And again, we may not have the full diameter drawn, so really what this tends to mean is we know that that chord goes through the center of the circle. So if we were looking at this same diagram and kind of going the other way about it, that was weird. Here we go. So if WB is the perpendicular bisector of AB, or I could use RS for this, then that means WZ is a diameter or goes through the circle center O. So if I just had this going through, a way I could tell if it was in the center is to see, or if it goes through the center, to see if it does bisect that chord. Alright, and then the last one of these theorems here. So if a, so in the same circle, or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So it says here, AB is congruent to CD, these chords, if and only if EF is congruent to FG. And remember, again, if and only if means it works both ways. So if we know that these are the same distance from the center, we know the chords are congruent. Or if we know the chords are congruent, we know they're the same distance from the center. And if you think about it, if you had a circle here, if you were to draw the chords going through it, what happens as you go up through the circle? The chords get bigger and bigger until you get to the diameter, which is the longest one, and then as you continue, they get smaller and smaller again. So it's the distance from the center that determines how long the chord is. So if they're the same distance from the center, then those chords would be the same length. Also worth mentioning, actually, before we try the problem, because this goes through the center and is perpendicular to this, that would actually also kind of apply our other theorem. So I would know that those two parts are congruent because it should be bisecting that chord. So there's another quick thought. So let's look at this in action here. So in this example, so in circle O, CD is perpendicular to OE, OD is equal to 15, and the length of CD is equal to 24. So we want to find the length of OE. Let's call that X. So it looks kind of like I've got a right triangle going here. And if I'm doing that, so if I'm looking at this right triangle, I'm not going to use 24 because that's this whole chord length, but because this is perpendicular to this chord, by our theorem, I know then that it is bisecting this chord. So these parts should be equal. So each of these little bits here is going to be 12. Now I can use Pythagorean theorem to find the length right here of OE. So we've got x squared plus 12 squared is equal to 15 squared. So x squared plus 144 is equal to 225. And we subtract 144, and we get 81, so x squared is equal to 81. Take the square root, and we would get x is equal to 9. Remember, not plus or minus 9 this time, because the distance can't be a negative. So x, or OE, rather, is equal to 9. Okay, so let's look at the next little bit here. So in circle P, the radius is 13, okay? And RS is equal to 24. Find each measure, round to the nearest hundredth, okay? So RT, right here, okay, that one's not so bad. So remember, because this is a radius, or it's going through the center and is perpendicular to this chord, it is bisecting this chord. So each of these pieces is 12. Alright, so let's look at this next set. So in circle P, the radius is 13, okay? And RS is equal to 24, so that full length of RS is 24. Find each measure, round to the nearest hundredth. Alright, so find RT. Okay, well this one's not so bad. So because this is coming from the center and is perpendicular to this chord, I know by our theorem that it is bisecting this chord. So that means that each of these is going to be 12. So RT is 12. Now we need to find PT. Right, this one right here. So we got to think about how to do this. So it does give us that the radius here, the radius is 13. But if I'm looking at this, I don't really see how that helps me. Because I could draw a line here to make a right triangle, but I don't know what this is. And I don't know what QT is, so that doesn't really help me. So this is a pretty common thing. The trick is that you can draw a radius wherever you want. So if I want to find PT, draw a radius to make this a right triangle, right? So if I draw a radius out here, that doesn't do me any good. But if I connect it to one of my other ones here, so let's go say right here, then I've got a nice right triangle here. But what's the length of this radius I just drew? Well, it tells us radius is 13, so I know that that's 13. So now I can use Pythagorean theorem to just find PT right there. And remember, hypotenuse is the one by itself, so we have PT, or x if you want to call it x. So x squared plus 12 squared is equal to 13 squared. So we start working this out. X squared plus 144 is equal to 169. And then we subtract 144. And we get that 25 is equal to x squared. Then we take square root of both sides. And we get that x is equal to 5. So 5, 12, 13 is a Pythagorean triple. Or rather, so x, aka PT, is equal to 5. Now that I know this is 5, I need to find the length of TQ. Well, this shouldn't be too bad, right? So we know that the radius is 13, so that total length is 13. So to find TQ, all I have to do is take 13 and subtract 5 from it that I just found, and that gives me 8. So TQ here would be 8. So that's how that goes. So always look out for that, because that is a pretty common thing to remember, that you can draw a radius wherever, and usually you can make a right triangle with it. Problems are pretty... Alright, the next two problems are pretty quick and straightforward, so we're going to go ahead and keep going. So number 4, in circle R, TS equals 21, UV equals 3x. What is x? Well, if we look at our diagram here, it's told us, hey, this is 6 and this is also 6. So what's true about these chords if the distance from the center is the same? Well, it means the chords are equal, so I can set these two things equal to each other. 3x is equal to 21, and then easy to solve, just divide by 3, and you get that x is equal to 7. Alright, number 5. So it tells us here that CD is equal to CB, and we know then that if these chords are equal, that means that they are equidistant from the center here. So GQ is equal to x plus 5, and EQ is equal to 3x minus 6. And because these chords are the same, we know that these two things should be equal to each other, so that allows us to set up an equation. X plus 5 is equal to 3x minus 6. And we want to get all of the x's over to one side, so subtract x. We get that 5 would be equal to 2x minus 6. Add 6 to both sides, so it would be 11 is equal to 2x. Then we can divide by 2. So we would get that x is equal to 11 halves, or 5.5. So that's it for those ones. I'm going to go ahead and cut this off here, and then we will finish the last few problems in one more video.